Allora, benvenuti tutti al terzo colloquio di Quidultra e oggi è un grandissimo piacere per me introdurre la nostra speaker Benedetta Ciardi. Ovviamente sarebbe stato ancora più bello se l'avessi potuto fare di persona a Roma, ma come per tutti gli altri speaker questo vuol dire che Benedetta potrà venire a Roma, speriamo, il prima possibile. E allora diciamo due parole su Benedetta, anche se ce ne vorrebbero molte di più. Benedetta è, let me switch to English, I'm sorry. So Benedetta is currently a researcher at the Max Planck Institute for Astrophysics in Munich. And but she started her scientific career in Florence. And she did her PhD thesis under the supervision of Andrea Ferrara. And since her PhD, her main interests have been focused on the investigation of cosmic reionization and the early universe. And following a pre-doctoral fellowship at the Center for Astrophysics in Cambridge, USA, and a Marie Curie postdoctoral fellowship, she has become staff member of the MPA, and there she has continued to accomplish her theoretical studies of the high redshift universe, and in particular through numerical simulations and of early structure formation, their feedback effects, and the exploration of by means of radiative transfer models. She has also been involved in different studies trying to infer observational signatures of the early universe through the infrared molecular line radiation emitted by the first stars, the detection of gamma ray bursts through the intergalactic medium, and the imprints of reionization on the temperature anisotropies of the cosmic microwave background radiation. On the nature of high redshift Lyman alpha emitters and damp Lyman alpha absorbers, and even on the detection of metals and dust in high redshift galaxies. And her academic achievements have been recognized with a Marie Curie Excellence Award and a knighthood of the Order of Merit of the Italian Republic. And more recently, her interests have turned on to the 21 centimeter line emitted by neutral hydrogen during various stages of reionization. And as this is one of the main activity of Benedetta in the past few years, she will focus her presentation on the exploration of cosmic reionization with 21 centimeter telescopes, as she is actually the responsible for the LOFAR antenna field hosted by the MPA. And we know that LOFAR is the main radio telescope based in Europe. So I leave the stage to Benedetta and encourage you to ask questions through the chat, even during the talk, and we will try to convey these to Benedetta. So please, Benedetta, go ahead.
Thank you, Raffaella. I'm really excited to not be in Rome, to have been invited, but it's really a pity not to be there in person. And I hope that, as you were saying, I'll manage to come sooner or later and to catch up with you guys. But I'm really happy to be giving this talk. So I will first give, sorry, but okay. I will first give a general introduction on the reionization process and the associated 21 centimeter line for those of you in the audience who are not familiar with the topic. And now I will give you a bit more details, in particular also on things that have been going on within my group and my collaborators. And in the end, I will also talk a little bit about LOFAR and give some news on this telescope. So here is the usual overview of the history of our universe, starting from the Big Bang. Initially, the universe is filled with hot plasma, and then following the expansion, the gas cools down and it eventually becomes neutral at an epoch which is known as recombination. Following which there is a period which is known as the Dark Ages, during which nothing, let's say, particularly interesting happens until the first structures and stars begin to form and emit the first ionizing photons, which initiate the intergalactic medium heating and reionization. And eventually, we think that this process of reionization is complete by redshift of about 6, and these initial structures which form evolve into what we observe today. Observationally, why do we say that the IGM, that the intergalactic medium, is ionized? Why do we talk about reionization? Historically, this comes from observations of high redshift quasar spectra, which show these characteristics, absorption features shortward of the Lyman alpha emission line, which are due to intervening neutral hydrogen between the observer and the high redshift quasar. And if you look at the optical depth of neutral hydrogen, you see that it is very high. So the fact that we actually observe some transmitted features means that the IGM is in a highly ionization state. And this is why we say that the IGM is ionized. And the first most stringent, let's say, constraints on reionization, again, came from observations of collection of high redshift quasar spectra. This is the not complete collection of objects above redshift 6. There are a few more that have been detected also at higher redshift. The record holder is now redshift 7.64 that has been recently appeared in the literature. And here you can see that as you move towards higher redshift, you have an increasing absorption along the line of sight due to the increasing amount of neutral hydrogen. So looking at this spectra, one can give an estimate of how much neutral hydrogen is encountered by the line of sight of these quasars and set constraints on these stages of the reionization process. As in the past decade or so, an increasing number of galaxies and even gamma ray bursts are being detected at these and even higher redshifts. These are similarly used to set constraints on the amount of neutral hydrogen around these redshifts. Another classic tool that has been used to set constraints on cosmic reionization is the cosmic ray background radiation. Basically the photons of the CMB interacts with the electrons that are produced during the reionization process, and anisotropies are induced on the CMB itself. The extent of which is described in terms of or quantified in terms of the Thomson scattering optical depth, which is basically an integral along the line of sight of the amount of electrons that are produced during reionization. So the Thomson scattering optical depth, this gives us an estimate of the global amount of electrons that are produced during reionization. What it doesn't tell us, though, is how these electrons are distributing through time. So when you hear somebody saying that observation of CMB tells us that the redshift of reionization is blah, 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 here there is some assumption on the reionization history behind, because as I was saying, all we know is only the global amount of electrons that are produced during the reionization. This figure just indicates a collection of some of the measurements through the years from the WMAP and the Planck satellite. So at the moment, these are basically the tools that we have to set constraints on reionization. And what we really miss is something that tells us with more precision how the reionization process evolved through times. And this is where the 21 centimeter line enters the picture. So the ground state of neutral hydrogen has a hyperfine transition. So basically this transition emits or absorbs radiation at 21 centimeter. And being a line, observations at different frequencies would give us information on the amount of neutral hydrogen at different ratios. So this would really be the ideal probe of the evolution of neutral hydrogen through cosmic time. And usually we quantify the 21 centimeter signal in terms of the effect that neutral hydrogen has on some background radiation that normally is the CMB. And it is described in terms of the differential brightness temperature between the CMB and the patch of neutral hydrogen with a given optical depth tau and spin temperature Ts, where the spin temperature regulates the population of the two levels of the hyperfine transition. So this is an expression for the differential brightness temperature, which is a function of the amount of neutral hydrogen, the CMB temperature and the spin temperature. Now, if the spin temperature is the same as the CMB temperature, this is 0. So in this case, you would observe nothing. If the spin temperature is below the CMB temperature, this is negative. So you would observe the line in absorption against the CMB. Otherwise, you would observe it in emission. So the value of the spin temperature is critical for the observability of the line. And this is given by a weighted mean between the CMB temperature and the kinetic temperature of the gas, where these two quantities here are the efficiency, the coefficients that describe the efficiency of Lyman alpha scattering and collision in coupling the spin temperature to the kinetic temperature of the gas, or conversely, decoupling the spin temperature from the CMB temperature. So the picture, the global picture that one expects is the following. This figure, the upper panel, indicates the evolution in redshift of the temperature. In blue, you have CMB, in black, you have spin, and in red, you have gas. And the bottom panel is the corresponding differential brightness temperature. So at high redshift, all these temperatures are the same, and so you expect to observe nothing. Then, as the gas temperature falls below the CMB temperature, because at this still high redshift, the gas is very dense, so collisions are efficient in coupling the spin temperature to the kinetic temperature of the gas, keeping it below the CMB temperature, so you expect to observe the line in absorption. Then, in the absence of other coupling mechanisms, as the universe expands, the density goes down, the efficiency of collisions is not enough anymore to maintain the two temperatures coupled, and thus you again would expect to observe nothing. But these range of redshifts are when the first object starts to form, and in addition to emit the ionizing photons that drive the reionization process, they also emit Lyman alpha photons. And Lyman alpha scattering is another efficient mechanism to couple the spin temperature to the kinetic temperature of the gas. So if you include their effect in your calculation, once again, you expect to observe the line in absorption. Through scattering, Lyman alpha photons can also transfer some heat to the gas. And once enough Lyman alpha background has built up, the temperature of the gas is raised above the CMB. And in this case, you have then a transition from absorption to emission. And in addition to Lyman alpha photons, you can also have other heating sources, for example, X-ray photons or cosmic rays or dark matter annihilation and decay, basically everything that can not fully ionize hydrogen, otherwise you wouldn't have the signal, but at the same time heat up the gas. Once the spin temperature is above the CMB temperature, then the expression for the differential brightness temperature becomes directly related to the amount of neutral hydrogen. So from here you see really how powerful this tool could be in estimating the neutral hydrogen content in the IgM as a function at various redshifts. Now, what I would like to underline here is that indeed 21 centimeter observation are a very powerful probe of neutral hydrogen in the IgM, but connecting the properties of the IgM to the properties of the sources that drive reionization is not an obvious step, because obviously you can have the same IgM properties, characteristics, which are determined by different source types. So you have some degeneracy there, and it's not straightforward or obvious to me that 21 centimeter observation could give you also very clear information on the properties of the sources. Now, from a theoretical point of view, what do we need to model the process? We need a model of structure formation that gives us the distribution of gas and of the property of the sources of radiation. And this can be done using your favorite tool, semi-analytic modeling, N-body or hydrodynamic simulation. Recently, these so-called semi-numeric approaches have become very popular, whatever. You need to know which are the properties of the source of ionizing radiation. There is a consensus that hydrogen reionization is driven by stellar type sources, but even for this type of sources, we don't really know which are the properties in the high redshift, and they can obviously impact the reionization process. And in addition to stars, we can also have contribution from different sources like black holes, X-ray binaries, or dark matter decay, annihilation, cosmic rays, and many others, even more exotic, have appeared in the literature. Finally, you need a way to follow the evolution of the ionized regions. And also in this case, there are a variety of different approaches, going from simple ones in which you count how many photons you have and how many atoms you need to ionize, and much more complex 3D radiated transfer codes multi-frequency, so that in the end you have a huge flavors of models of reionization that go from fully semi-analytic one, in which basically you follow and model the average properties of the IgM, and these are very useful because they're quick and you can explore a huge parameter space without any problem. And at the other end of the scale, you have fully radiated transfer hydrodynamic simulations coupled, which are great tools as well. But obviously they have as well to rely on some assumption. For example, radiated transfer will not be done in a super accurate way, or the boxes of simulation boxes are not extremely large, because obviously these sort of simulation are extremely computationally intensive. And then obviously there is anything in between. So my view on these is that every approach has its merits, and the approach that you use very much depend on the type of problem that you want to address. So everything is useful, and I'm not focused on one rather than the other. In our group, though, usually I'm going now to present a little bit in more detail the approach that we use typically in our group, and in particular I will describe simulations of reionization that have been mainly run by Marius Eide, with also some addition by Silvia Fiaschi. So what we normally do is to use hydrodynamic simulations to model structure formation. We have a number of different simulations that we have used to address different problems. The ones that I will mention now have been run in the group of Tiziana Di Matteo and Rupert Croft in Pittsburgh. They're described in Kandahar and collaborators, and they are the massive black too. And from our point of view, these are ideal simulations because they cover a relatively large simulation box of 100 comoving megaparsecs. They have a very high numerical simulation, numerical resolution, so that we are able to resolve the objects that produce the bulk of the ionizing radiation. But even more importantly, they follow as cell-consistently as possible both stellar type sources and black holes. So this means that we are able to include as models of ionizing sources of ionizing radiation, stars, single stars and varying stars, although the results that I'm going to show are just from single stars, nuclear accreting black holes, X-ray binaries, and shock-heated interstellar medium. And just to give you an idea of how the spectral energy distribution of these sources look like, is shown here in this plot, where colors refer to different redshifts, although the redshift dependence is really not very strong. So these dashed lines refer to the stars, the stellar contribution, which dominates as expected for ionization of hydrogen and singly ionized helium, while for in the energy regime interesting for full ionization of helium, the interstellar medium, shock-heated interstellar medium, is the most relevant source. And finally, the X-ray binary contribution is important at the highest energies covered here. So to each galaxy, we assign a spectral energy distribution, which is given by this solid line here. It's the total contribution from these source types. And whenever a black hole is active within a galaxy, that's considered as well, and it actually dominates the ionizing photon production, although when you evaluate the cumulative emissivity from the different source types.
Devi fare adesso, meno male.
Prima no?
No.
Is there a question? No? Okay, then I keep going. As expected, the cumulative emissivity is dominated by the stars, while interstellar medium and X-ray binary are really negligible, given negligible contribution. The black hole's contribution, increases with decreasing redshift as the population of black holes becomes more substantial. Just to be clear, these two lines, solid and dashed line, refers to the escape fraction of ionizing photons from the galaxies, of UV photons from the galaxies, which is basically the only real parameter that we adopt in our simulation. And the solid one refers to a 15% constant escape fraction, while the dash one refers to an escape fraction which decreases with decreasing redshifts. Now, one thing to keep in mind when including energetic sources into these sort of models, one has to double check that their cumulative contribution does not exceed measurements of the X-ray background at lower redshifts. This we have done this check. Here I'll just show a summary plot showing the X-ray flux from redshift above these values here. The upper panel refers to the 0.52 keV band and the lower panel to the 2.8 keV band. You see that, as expected, that the most of the contribution comes from the X-ray binaries. And if you look at the flux coming from a redshift larger than 5, which is this black number here, and you compare it with what has been estimated from Chandra observations, so the residual X-ray background expected to come from redshift at high redshift, you see that we are always roughly an order of magnitude below this observational constraint. So this means that in principle, the contribution from high redshift energetic sources to the reionization process could be higher than what we assume or that we have in these simulations. In particular, the contribution from black holes at high redshift is highly dependent on how the black holes are modeled, so how they are seeded into the simulations, and clearly different seeding procedure could give very different results. And this is something that we have started to look into. If you want, you can refer to this paper here, but I don't have time to discuss this in the talk, although if you're interested, we can talk about this later on. So going back to the modeling, the last ingredient that is needed is, as I mentioned, is a way of following the evolution of the ionized regions, which we do in processing using a 3D multi-frequency radiated transfer approach called CRASH, which is continuously under development within our group. And what I would like to highlight here is that this is really a multi-frequency code. It just doesn't have 3 frequency bands, but it has 82 frequency bins between 13.6 electron volt and 2 keV. This is particularly important if you are interested in considering also the helium ionization, which we have in this simulation, and for a correct evaluation or as accurate as possible evaluation of the temperature of the intergalactic medium. Now, let me show you some representative results from the simulations, which highlight the impact of different source types. So these are slices cut through the simulation box at redshift 7.5. They don't show the full box, but they are focused or concentrated on a massive black hole, which is located here. The upper panel, the first column refers to a simulation in which we have only stars, then stars and accreting black holes, stars and X-ray binaries, stars and interstellar medium, and all sources together. The upper panel refers to the fraction of ionized hydrogen, and the lower panel refers to the difference in comparison to the case with only stars. Red means that you have more ionization, blue that you have less, and when you see these blue and red pixels, they're due to Monte Carlo noise. So as expected, you see that the full ionization of hydrogen is driven by stars. You have a slightly larger extent of the fully ionized region when a strong black hole is present, while sources like X-ray binaries or interstellar medium just produce this partial ionization outside of the full ionized region, with interstellar medium being more efficient due to the spectral energy distribution. The behavior of helium-2 is very similar to the one of hydrogen, with a difference that around the location of the more energetic sources, strong sources like the black holes, but also some of the X-ray binaries, you have a lack of helium-2. And this is just because it has gone into helium-3. And here indeed is where you see, as expected, the strongest impact from the more energetic sources, with the black holes being able to fully ionize helium, while X-ray binaries and interstellar medium, again, producing this partial ionization of different intensity, depending, once again, on the spectral energy distribution. Temperature, again, has a very similar behavior to hydrogen. So within the fully ionized region, the temperature is mainly driven by stellar type sources, with the exception of the location, again, where you have very strong sources, where you can see, for example, here for the black holes, or here that you have a lot of red, meaning that you have hotter gas. And again, X-ray binaries in interstellar medium produce this warm gas outside of the fully ionized region, corresponding to the partial ionization, which, as we'll see later, is relevant for 21 centimeter studies. As a sanity check, once you have your models of reionization, you should also compare to some standard observation. The one is the Thomson scattering optical depth that you see here on the left. This is evolution in redshift, and as you see, all our models basically overlap. So, and this again is expected because most of electrons are produced. Full ionization is produced by stars, so the other sources don't have a really strong impact on the cumulative number of electrons. On the right, instead, I show a comparison to the measured neutral fraction at various redshift. So first of all, you can see that even not always there is a convergence or agreement between different observations. But in any case, the simulations are very well consistent with observation down to redshift 6.5 or so. But towards the end of reionization, they don't really match anymore. And this is basically due to the fact that when most of the IGM is ionized, it's important to include the effect of Lyman alpha emitters on small scales that can be sink of ionizing photons. But the scale of the simulations, the resolution is such that we cannot resolve the Lyman limit systems, and we decided not to include any subphysics in the simulation to take them into account. So that's why we don't match any more observations towards the very end of reionization. But in any case, there is a good agreement, and in the original paper you can find also comparison to other observations if you're interested to look at them. So once you have a model of reionization, these one or others, then obviously you can also estimate what you expect in terms of 21 centimeter signal. Now, first of all, what can we do with that 21 centimeter signal? So the holy grail of people that are working in the field is the possibility of doing imaging, because this would give you the distribution in time and in space of neutral hydrogen, so that you could really study the topology of the ionized region, the history of ionization, and possibly, with some reservation, as I mentioned earlier, gather information also on the sources of ionizing radiation. And this is something that an instrument like the SKA is designed to do, while the present generation of radio instruments, telescope and interferometers aims at detecting statistical quantities. But even statistical estimates are extremely valuable, as I'll mention later on, in constraining and gaining information on the reionization process. It has been suggested to do with 21 centimeter the equivalent of the Lyman alpha forest. So if you have a radioloud source, you can study the absorption in 21 centimeter along the line of sight and gather information on neutral hydrogen. And it has become an increasingly popular the idea of using 21 centimeter observation in combination with observations in different frequency bands for multiple reasons. First of all, it has already been demonstrated that using different type of observation can help reducing systematic effects. You could confirm the origin of the signal, which is something needed as the signal is tiny. And it could help gaining information on the sources of ionizing radiation. Now here I try to give comprehensive literature on the various topics, but it's far from being really complete, as especially in the past few years. Papers have really, the number of papers have exploded, but in any case, this should give, cover the various topic quite extensively. I'll now touch briefly upon each of them before talking a little bit about LOFAR. So in the category of imaging, high-energy imaging, there is the possibility of detecting ionized region produced by quasars and possibly gaining information on quasars themselves. This is something that has been studied recently by Koke Kakichi and Jingmo Ma, using, again, simulation of reionization, similar to the one that I mentioned earlier, although focus on high density region to sort of mimic the environment where one would expect to find a quasar. So simulation with stellar type sources have been run, and then for the case that I'm showing now, a quasar has been switched on a redshift 10, producing the ionization pattern that is shown in this figure. So once you have this, you can also evaluate what is expected in terms of 21 centimeter signal. So the bottom panel shows a case in which only the contribution from galaxies and stellar type sources basically is considered, and the upper panel in which also the contribution from the quasar has been included. The left panels refers to the case in which we assume that the spin temperature is much larger than the CMB temperatures, so everything is emission, while on the right, the spin temperature is the same as the gas temperature, so there is no assumption there. So the first thing to note is that if you are in a situation in which the signal is just in emission, there is no obvious signature pointing toward the presence of the quasar. So this big region here could be just produced by a number of galaxies. There is no obvious, really obvious, clear signature of the presence of the quasar, especially once you convolve these theoretical expectation with the instrument characteristics. On the other hand, if you don't make this assumption and you get the case in which the spin temperature is equal to the gas temperature, you see that most of the signal when only galaxies are present is in absorption, while this ring of emission is produced by the high energy tail of photons emitted by the quasar, which partially ionize and heat the gas surrounding the fully ionized region. So in this case, and unfortunately though, most probably, in the real world, there will be in this situation, because in addition to stellar type sources I mentioned earlier, you can have shock-heated interstellar medium X-ray binaries or other sources that would raise the temperature outside of the fully ionized region. So most probably will be in this case. So although this sort of large high-redshift ionized regions should be detected by an instrument like SKA, and it will be great because we'll still gain information. It's still not clear whether you could distinguish or the origin again of these ionized regions just looking at 21 centimeter signal. In terms of statistics, we have used the simulations that I mentioned earlier to study, once again, the possibility of detecting signatures from different source types. These are the same simulation that I mentioned before in 21 centimeter. At a relatively high redshift, the signal is very similar. Because it is dominated by the stellar contribution, and the impact of the more energetic sources is still not clearly visible. As you go down in redshift instead, first of all, you see that the interstellar medium that has produced warm gas outside of the fully ionized region has rendered the signal completely in emission, while when you have only stars or also black holes, you have still a lot of absorption. X-ray binaries is something in between. These impact can be seen more quantitatively in the evolution, for example, of the volume average differential brightness temperature, which again at the highest redshift is the same. And then at a certain point, you have a transition from absorption to emission whenever you have heating from, for example, interstellar medium again and X-ray binaries. But this transition happens at different redshifts depending on the source type. While for the stars, the signal or the average signal remains always in absorption. This can be more clearly seen here, where you have the the expected probability distribution of the differential brightness temperature, broken up at different redshift and for the various models. And again, you see that this peak of the distribution goes from absorption to emission at different times depending on the source types. The impact of different source types can be seen also on other statistics. For example, the classic power spectrum, which I show here as a function of redshift for 3 different Ks. Once again, at high redshift, everything is the same, and at a certain point, you see the clear impact of heating from the more energetic sources, which reduces the intensity of the power spectrum. Similar but much more complex behavior can be observed in the bispectrum. I'm not attempting to explain why one can observe the different features, but if you're interested, we can discuss more about these later on. But the bottom line that I would like to highlight here is that different source types have a characteristic imprint on different statistics associated to the 21 centimeter signal, so that using different statistics could help into breaking, at least somewhat, breaking the degeneracy that we would expect from different properties of the sources of ionizing radiation. I mentioned the possibility of studying 21 centimeter forest, and again, the idea is having a high redshift radio loud source and detecting the absorption along the line of sight, which would give the spectrum similar, let's say, to the Lyman alpha forest. Now, because the optical depth to 21 centimeter is given by this expression, to have a strong absorption, you need to have a pocket of gas with which is neutral, has a high density, and is cold. And these pockets of gas, in principle, can be found also towards the end of reionization. So here I show a case at redshift 7.6, but even at lower redshift, you can find, you can theoretically expect absorption features in 21 centimeter that could be in principle detecting. This is just an example in which the background source has characteristics similar to the Cygnus A and is located at redshift 7.6, and the intrinsic spectrum is this red line here. In blue, you have the theoretical absorption spectrum, and in black, you have what LOFAR would observe in 1,000 hours of observation. So you see that, you know, in principle, it could easily detect these very strong absorption features due to one of these pockets of gas that I was mentioning earlier. But the real problem is that there is a lack of high redshift radio loud sources. Actually, just yesterday on the archive, there was a paper by Banados and collaborators mentioning the detection or the discovery of a source at redshift 6.82 with a flux of the order of a few millijansky at 150 megahertz, which is great, although it's still probably not enough, but it's you know, it's a great step forward in this direction. And it is interesting that, you know, in the past few years, a few of these still not extremely high redshift, still not extremely bright radio sources are being discovered. But if more of these sources were detected, then one could think about stacking them rather than, you know, counting on having a really bright radio source to stack a few tens of them, and maybe this would become an actual possibility. And it's something that LOFAR or MWA or SKA could in principle do. The last thing I would like to mention before moving to LOFAR is, as I said, the possibility of using 21 centimeter in combination with other observations. And this again has become extremely popular in the past few years. And the most promising, now I'll just mention a few again, not going into details, but I just want to give you a flavor of what can be done. So the most promising cross correlation is with high redshift galaxy surveys, specifically Lyman alpha emitters. And because galaxies host the sources of radiation, so they reside in ionized regions, while the 21 centimeter line is associated to neutral hydrogen. So we expect a certain redshifts and scales to observe an anti-correlation. And it can be used in multiple ways, and for example, to give an estimate of the typical dimension of ionized regions at a given redshift. And this is a possibility that has been explored by a number of authors, and it looks feasible with SKA, for example, and Subaru or WFIRST. It's something that indeed could become a reality. But not only Lyman alpha emitters could be used, anything that in the end, you know, traces the galaxies. And as more galaxies recently have also been associated with high redshift metal line emission, this could in principle be used in a similar way. It has also been suggested to study correlation with integrated quantities, such, for example, the cosmic microwave background radiation, or the infrared or X-ray background. And in these latter cases of the infrared background or X-ray background, the background encodes also the properties of the sources that make them up. So the behavior of the cross correlations would depend on redshift scales and also the source properties. So once again, we could use these sort of observations to try and gather information on source characteristics. So the bottom line is that if we use, you know, all these different combination of observations and the statistical properties of the 21 centimeter signal all together, we could indeed start also gathering real information on source properties in addition to properties of the intergalactic medium. Now, because of these, you know, great promises, there are a number of instruments that are, yeah?
5 minutes.
Yeah. that are being that are trying to detect the 21 centimeter signal, among which the LOFER telescope, which is based in the Netherlands, but has a strong collaboration from a number of countries all around Europe, and Germany is contributing with 6 stations. Each station has a low band antenna field between 20 and 80 megahertz, and a high band antenna field between 115 and 240 megahertz, which is what is interesting for the for reionization studies. And MPA itself is hosting one of these antenna fields. This is an aerial view of the field, which is actually quite unassuming, but that's it. The first upper limit from LOFER appeared a few years back based on one night of observations of the North Celestial Pole, which is the main field observed by LOFER. The upper limits were given at different Ks, and in three different redshift beams. A few months ago, revised upper limit at redshift 9 was published based on 10 nights of observation. And as you can see, the numbers have gone down quite a lot. Actually, now the lowest upper limit is given by NWA, which is, I think, 40 something square milli-K squared, but that's at a much lower redshift of 6.5, something like that. Now the plan is, okay, before going to the plan, it's really exciting that despite the upper limit being still relatively high, or higher than what we would expect from theoretical models, we actually start using them for real. So this is a realization of a number of power spectra. There are about 10,000 power spectra covering different models of reionization. The blue line corresponds to the reionization model depicted in these maps here to the right. And these red dots indicate the upper limits from LOFER. So you see that there is here a corner which is actually excluded from the upper limits. And although these are extreme reionization models with very cold IgM, which we already knew that were not extremely realistic, it's actually very exciting that we can really start excluding some theoretical models and using these observations to guide our models. The plan now is to analyze the same 10 nights at other redshifts, so specifically redshift 8 and redshift 10, and then to go deeper at redshift 9, which seems to be the sweet spot for LOFER, analyzing 100 nights. Not clear when these new data will be available. Usually as you start going deeper, you find new systematic effects and needs to be taken care of. But it's great that that these observations are really becoming real. So I'll leave you with my conclusions, and if I'm over time, actually, you can just read them, and I can finish here. Thank you very much.
Thank you, Benny. Thank you for this beautiful presentation. A lot of work and still a lot of excitement. Looking forward to new LOFER data. So I open now the discussion, and if there are questions, Fabrizio Nicastro has a question, so you can switch on your mic, Fabrizio, and ask the question directly.
Yes, hi Benedetta, very nice. Thank you. I do have actually a couple of questions. One is something probably I didn't understand when you mentioned stacking spectra of background regular QSO. But then you are, this is exactly the same technique you use for the Lyman alpha forest, exactly. I mean, you look for 21 centimeter line in absorption, but those have different redshifts along different lines of sight. So how can you stack and improve the signal?
No, you're completely right. You know,
Okay.
this is not something that can be done now, because there are two basically two observations of objects that in principle could be used, but they're not they're not close enough in redshifts. So to be able to do something like this, you're completely right. You need to have a much larger sample and you know, at the similar redshift. Otherwise, this is not feasible. But
then I have another question, and if I may, a comment. The question is, how critical are the assumptions you do in other hydrodynamical simulations on, in particularly on the black hole? Because I think black holes are very important, as you showed. So in particular on the seeds that you use and the duty cycle of black holes. Because don't make the duty cycles in particular, I mean, my impression is that it may change completely the patchiness of the medium, because they switch on and off.
Okay, so it definitely it is highly dependent, and in fact I'm planning to run also other simulations in which the seeding is done differently, because this is the standard assumption in which you have 5 10 to the 5 solar mass black holes seeded into 5 10 to the 10 halos. Okay. And but clearly you can have you know, smaller black holes within smaller halos. So two things. First of all, these certainly would change things at high redshift and could increase the contribution of black holes. As I was mentioning, we have started to do this using some basically neural network approach to populate the halos in the massive black 2 with smaller mass black holes. I'm not going into details. If you want, we can talk about this. But basically what we find with this preliminary approach, I would say, because it's just a preliminary study, is that if we do this, doing a simple semi-analytic calculation of the reionization process, we find that this blue line is what we obtain when we consider these smaller mass halos populating small mass objects, compared to this black line here, which is given by the black holes presently. Sorry, there is it pops up automatically, which are present now in the massive black 2. So you go from you know, a contribution of 0.2 of the H2 filling factor, 20% present, to you know, almost 60%. Stars are still dominating.
Right.
And this is an upper, I think it's an upper limit.
Okay. Very interesting. Then, Raffaele, if I may, just the 30 seconds. No, then, okay.
That just leaves some time to others.
Sure.
So there is a raised hand from Gianni Bernardi. So Gianni, please go ahead.
Ciao Benedetta.
Ciao Gianni.
Oh, ciao. Lovely talk. That's good to see you. I think we've had in the past this conversation. What am I about to ask? But so, okay, let's assume that one day we measure something like the evolution of the neutral fraction of the IgM or some basic quantity. Do we have a consensus of what we can learn about the underlying physics of sources, in the sense like, you know, like, I don't know, mass of galaxies that reionize the universe without being degenerate with the ionizing efficiency or whatever, something like this?
No, Johnny, you know what I think about this? My answer is no. I don't believe we can do that. I think we can learn whatever you want on the properties of the IgM, and that will be fantastic. But we cannot infer with certainty properties of the source of ionizing radiation, because there is too much degeneracy. I think we need to use different, aided by different observations. And yeah, even then, I wouldn't make a huge bet on that. I think we can constrain. Yes, we can start setting some constraints, but having a certainty. Also, you're mentioning the mass, the minimum mass of the objects. I mean, to know that, we would need to know, for example, also details of how feedback processes work, which, it's a topic that has been going on forever, and I think we'll keep.
Yeah, sure. I was just saying.
So, but it's good, because then we can keep studying and learning.
Thanks. Okay.
So, if I may add a comment before asking for other questions from the audience, the comparison that you're showing here, of course, relies on how also you model the stellar emission itself and how this varies with redshift. And if I understand correctly from what you said at the beginning, the SED that you are assuming is essentially the same for all galaxies. You don't have a redshift dependence, let's say, from stellar populations that may change, the metallicity may change.
So we actually have that, in the sense that we have modeled every single stellar, assuming that the hydrodynamical simulations are correct, and that there are assumptions there, right? So whatever, we can't do everything, but we have evaluated the spectral energy distribution of each stellar particle.
So the
yeah, and then what we have done, we have studied the dispersion basically. And in the end, because the dispersion was not huge, it could be easily convolved into the uncertainty contained, for example, in the escape fraction. And so we have decided to adopt an average SED for each galaxy at each redshift. But before that, we actually did a quite extensive study of those dependencies, which actually I'm not sure why we didn't include in the paper, because it's something by itself quite interesting.
Yeah,
we can do it, can do that.
So if there are no other questions, I would give again the time to Fabrizio to make his final comment. So Fabrizio, go ahead.
Thanks a lot, Raffaella. Thank you very much. The comment is about, I think, Benedetta, I think we were both at CFA at the time when the National Radio Observatory in the US was about to actually shut down radio astronomy completely, because the game was becoming very tiring of people looking for blobs of superluminal quasars and things like this. And the most brilliant idea back then was exactly to look for the IgM high redshift with a 21 centimeter line. Now it seems to me, and there was a revival of all this game, and new observatories planned. LOFAR is one of these, SCA, and many others. Now, my comment is essentially that it seems to me that way too many years have passed since the great idea to now, and we still now don't have a single photos of these probes of the high redshift universe. And in a sense, you spend most of the talk saying, yes, we will have a great picture of the IgM, the neutral hydrogen at high redshift, which is indeed very important, but you still need to sell to the community these in another way, talking about the sources, things that probably you will never be able to do. So I think this is it's just a comment. I mean, I don't have any opinion on this, but my impression is that really, if it takes 30 years from the idea to the first photons, or more than 30 years, then it becomes out of fashion, or I don't know how to say that, but we have some problem.
Well, so actually, when I was at CFA, the thing I remember is the failed Chandra launch more than the radio. The radio. I was not into the radio yet.
A bit before that, yes.
that I don't remember, but so I started to get involved in LoFR basically almost from the beginning, and it was at the beginning of 2000. And I mean, this is really hard business. You know, you don't count in X-ray astronomy. You basically can name every single photon almost. You know them by heart. Radio astronomy, which despite all these years I've been in contact with radio astronomers, help Gianni, I still don't understand. It's really hard. And the problem is that the signal is so tiny that every time that you, so the LoFR team, I can tell you that because it's the one that I'm more in contact with, has gone insane with calibration. Insane. It took basically 10 years to get to a level of calibration that was satisfactory. And and the sky model, it took, they had to use so many sources for the sky model, which probably will not be good enough once you start analyzing more data, and you go even lower, and you'll find new challenges. So it's really hard. And I completely see how people can get demoralized. There are some people that are still very excited, and that it's good to have these people. But I don't see another way of really learning about the intergalactic medium. So it's true that you don't learn maybe about...
No, but I wasn't a criticism to that. I fully agree with you. I'm only saying that we probably spend too much. I mean, it is hard. It is hard to do. Even in X-rays, it's the same. I mean, we launched Chandra in '99, and still the new Planck telescope is no earlier than 10 years from now. So 40 years later. It is too long.
Yeah, but for example, now you see, eROSITA, you had fantastic results, like basically 2 days after the launch. This will not happen with SKA, by the way. Maybe I shouldn't say it, but it's not going to happen. Even with all the previous experience developed with these precursors, SKA will still have challenges. So it's not going to be the same, even
I can add a comment to Fabrizio's comment. Think about gravitational waves. It took a century from the great idea to the first detection, and I still think that it was worthwhile, and I think that none of us would doubt about the fact that it was worthwhile waiting for the detections. So I don't know if there are other quick questions, but if not, I would really like to thank Benedetta again for her fantastic talks. And so if you want to unmute your mic, we can give her an applause all together.
So, thank you for having me.
And I really look forward to having you here personally in Rome.
I'll come as soon as it's possible. I'll come.
Okay, so thank you all for attending, and we'll meet soon for the next Quidulta colloquium. And I think we can all leave the room, but the PhD students who have some extra time with Benedetta to chat. Okay.
Bye, everybody.
Ciao.
Bye.
Ciao, ciao.
Ciao.
Ciao, Benedetta.